And also let you know, Aseem, the students or the participants can't unmute themselves. So if you want to take any questions, so you have to do it.
That's fine. Okay, so it's 2:30. We can get started. So this is going to be a lecture series which is more or less a continuation of what Surhud was talking about. He was giving you an introduction to basic cosmology. So this lecture series will deal with formation of structure in the universe. And many of the things that Surhud spoke about may either play a role or they may get repeated a little bit. So there will be some overlap with what he spoke, but mostly this will be a continuation of that set of topics. And broadly speaking, what one would like to understand is how structure grows in the universe. So on the right-hand side, you have a picture which is a map of galaxies in the nearby universe. So you've already come across this idea of redshift and how redshift is a distance indicator. So this is redshifts of roughly 0.1 or so at the outermost edge of this plot. This is from the Sloan Digital Sky Survey. Every point is a galaxy. And what you can see is that there is an organized structure in the way galaxies are distributed in space. This is called the cosmic web. And what we would like to understand is how this kind of structure, which is observed in the universe, emerges from what we also know from other observations to be the initial conditions at very early times in the density field of the universe. So this image on the left is taken from the Planck satellite. This is a map of the anisotropies in the temperature of the cosmic microwave background, which also I believe you would have heard about. And this is a snapshot of the universe, if you like, as it was when it was around 400,000 years old. And this, if you like, is a snapshot of the late time universe when it is around 13.7 billion years old. So we would like to know how the universe went from looking like this to looking like this. Okay? And that is broadly what structure formation is all about. This particular lecture will deal with, so I have 3 lectures. Lecture 1 will be about how these initial conditions, how these tiny fluctuations came to be. I will give you a broad introduction. So I would just like to mention that this lecture series is going to be at a fairly broad level. There will be equations, but I will not be presenting many derivations, not any actually. But I will instead give you, right at the beginning, a list of useful literature in cosmology. So this is not just for structure formation, but for cosmology in general. And I have listed here books which I have personally found very nicely written and very useful, all of them here. This is not a complete list. It is a very, very biased list. It is my own personal choices that are being reflected here mostly. And among these, I have highlighted a few which were extremely useful to me as a student. Okay, this one is a bit late for me. It came out only 2012. But these two, Narliker's book and Dodelson's book, they were extremely useful to me. So that's why I thought I'd highlight them. And the book by Moe, Van Bosch and White is nice because it is, to date, it is the most up-to-date version of structure formation, galaxy formation, etc., these topics. And these authors in particular, Ho-Jung Moe, Frank van den Bosch, and especially Simon White, they have, in either individually or in collaboration, worked on almost every conceivable topic in this particular field. So this is a book worth having. These other 2 books are very nice as introductory material for basic cosmology, as in the case of Narliker, and for early structure formation, as in the case of Dodelson's book. Okay, so let me give you another kind of picture. What I showed in the first slide was the observational point of view. This is a simulator's point of view of how structure might grow in the universe. So what you saw here, if you paid attention, was that early on, the density of this box was very low. Okay, and it was basically a very uniform looking medium here. And as time progresses, so here we go, it's looping back. So it starts by looking very uniform, but then as time progresses, there are places in this box where the density becomes very high. So this is a logarithmic scale here. So between red and the blue, there are at least 3 orders of magnitude, okay, in density. So there are places in the universe which become very, very overdense. And there are places like this huge region here, which are going to become very, very underdense. Okay, all starting from relatively uniform initial conditions. So this is gravitational instability at work, and we would like to understand this mechanism. And we also want to basically understand how this whole scenario plays out in the presence of certain initial conditions, where these initial conditions came from, what they tell us about the early universe. And then as this growth progresses, what this growth tells us about what the universe contains, for example. So some of these things I believe Surabh touched upon. So this is going to be the theme of this lecture series. And in the first lecture, I am going to deal with the initial conditions, and in particular with this mechanism called inflation, which is believed to be the source of these initial conditions. So let me also just say that I guess you guys are now already familiar with asking questions using the Google form. So please do that, because while I am in this full screen Zoom mode, I cannot see anybody. So at the end of the lecture, I will just open the Google form. I will stop sharing my screen and I will take questions. I hope that works out for you. And in any case, if something is left over or not clear or something, at the beginning of the next 2 lectures, I will maybe spend some time addressing questions from the previous lectures. Okay, so let's move forward. We would like to understand where these fluctuations in the initial conditions, which I showed here. So think of the cosmic microwave background anisotropies as setting the initial conditions. But we would like to know where these tiny fluctuations came from. What happened before this time of 400,000 years that set these initial conditions in the first place? Okay, so that is today's lecture. And in order to do this, I would like to start with something slightly different. Okay, so before talking about the perturbations themselves, let's go back to the standard model of cosmology. You remember from Suraj's lectures that the standard model has several components. So there is a background cosmology, which is defined by several smooth components. There is ordinary matter, there is some dark matter. Both of these behave non-relativistically for most of the history of the universe. Then there is radiation, the photons, using which we see things, and other species of relativistic particles such as neutrinos, and also the standard model baryonic components. So for cosmologists, baryons means anything that is, anything that is part of the standard model of cosmology. Leptons are also baryons for us. So things like electrons, protons, etc. They also, in the very early universe, as Surud would have told you during Big Bang nucleosynthesis and later, these species were also relativistic. So they contributed to a relativistic medium at early times. Some of them, because they are massive, they eventually became non-relativistic as the universe expanded and cooled. And today we have a mix of all of them. And of course, then we also have these strange, mysterious things, which is dark matter, which we cannot see, and dark energy, which is probably a cosmological constant, but we do not know for sure. But for whatever it's worth, this is the standard model of cosmology. And what I would like to start with is a couple of issues in this standard model. Even if you forget about the fact that we don't understand dark matter and dark energy, we at least understand electrons and protons and other baryonic species, and we understand radiation. So let's focus on the early universe, where these were the only things that were around. At least radiation was a dominant component. And let's see what problems there were with this picture. And then because of the problems that I will describe to you, I will then move on. Basically, these problems will say that they need a solution. So in the context of these solutions, we will come across the idea of inflation and therefore something that sets the initial conditions as well. Okay, so let's start with something which is very basic and very interesting, even if you're not interested in structure formation. This is an interesting aspect of cosmology in general, which is the idea of horizons. So the interesting question to ask here is the two of them. One is, how far can you see? Okay, this is actually a very general question. It has been asked by many people across history. Sailors who went out on ships would ask, how far can we see? Okay, how far is the horizon? So the name horizon is something that tells you about how far you can see. And a related question in cosmology is, how far can you throw? So how far can you see is something about signals coming to you from somewhere. So from how far can signals reach you? And how far can you throw is a question about, if I sit here and throw out a signal, how far will that signal reach? And in cosmology, these two things can be addressed separately. The answer to the first question, how far can you see, it goes by the name of the particle horizon. And the answer to how far can you send signals goes by the name of the event horizon. So these are general concepts, not just in cosmology, in general relativity also these ideas will come up. We are speaking in the cosmological context. So let's talk about the particle horizon first. I will also discuss the event horizon, but this will play a smaller role in the discussion later. So let's talk about the particle horizon to begin with. So the particle horizon is defined as the maximum co-moving distance that material particles can traverse. Okay, so if I take a stone and I throw it, how far can I throw it? In general, in full generality, how far could I throw it? Assuming I have access to all possible, power in the universe to accelerate things or whatever. So what is the maximum co-moving distance traversable by material particles, which were given an initial kick at time t equal to t naught, until some time, at time t equal to 0 for the initial time, and until some time t equal to t naught. So if these particles have been traveling with some speed, how far could they have come? And of course, the speed of light gives us a upper limit to this distance, because nothing can travel faster than light. So all I have to do is to ask, how far will light travel from t equal to 0 to t equal to t naught? And that gives me the answer to what is the maximum distance a material particle could have traveled. And in order to know how far light would travel, I have to go back to the metric, which Surud would have introduced to you. So the line element, ds squared, which I have not written here, but I hope you have notes on this. You know that the trajectories of light using this metric are given by solutions of the equation ds squared equal to 0. Right? So the line element equal to 0 is the description of the trajectory of light. So you set ds squared equal to 0, and then you will get an equation between the co-moving distance and time, and you can integrate this equation, and what you will get for the co-moving distance from time t equal to 0 to t equal to t naught is this expression. You've probably already seen this in some form in the previous lectures. And this quantity, because it is ultimately just give me 1 second, I'm getting some. Sorry about that. Okay, so this quantity, this particular integral, you can show that it is always finite. Okay, in any cosmology, this will be finite because ultimately it's just an integral over space of a particular trajectory. And this, you can write it in different ways. For example, here I have converted from this time to the redshift, because what I can do is I can write this dt as dt divided by dA times dA divided by dz times dz. Okay, and A is the scale factor, Z is the redshift. So now dt divided by dA is 1 over A dot, and A dot I can write in terms of H, which is A dot by A. Okay, so there's an A dot sitting around here. Then the other thing was dA divided by dz, and A and Z are related to each other as A equal to 1 over 1 plus Z. So I can convert from A to Z in a very simple way. So I invite you to check this equation when you do this integral, starting from 0 to t naught. There will be some signs which have to be adjusted, because somewhere there'll be a negative sign. You have to invert the integral limits, etc. And then this 0 is actually corresponding to z of infinity, and this t naught is corresponding to a z of 0. Okay, so today is redshift 0, and time t equal to 0, which is the Big Bang in this way of thinking, corresponds to infinite redshift. So this particular integral is what you would like to evaluate. And the reason to write it like this is because in a standard cosmological model, Friedman's equation tells me how to write h as a function of z, parameterized by numbers like omega matter at present time, omega radiation at present time, omega lambda at present time, and so on. So what I've done here is to just take some standard cosmology, a flat universe with some standard omega matter, omega lambda, and at least get an order of magnitude estimate. And what you will find is that this quantity chi, which is this co-moving distance, is of the order of 10 gigaparsec, 10 h inverse gigaparsec. Okay, this little h is just a parameterization of the Hubble constant. So h0, which is 100 kilometers per second per megaparsec times little h. Okay, so the actual Hubble constant is probably close to 70. So this little h will be a number of the order of 0.7 in a standard cosmology. So this is the particle horizon. Okay, and this particular thing is not necessarily the co-moving distance. This is equal to the co-moving distance for a spatially flat universe. But if the metric, if the FLRW metric has a spatial curvature, then you also have to do one extra step where you do this integral. And then remember, there is this function which is sine or sine hyperbolic, depending on whether the sign of the curvature is positive or negative. So you have to apply that transformation to get the co-moving distance from chi. But throughout this talk, let's just assume that the universe is spatially flat. I will have a little more to say about this in the next couple of slides. And then this is the particle horizon. Okay, and this is a useful number to remember if I ask for the particle horizon, which is from how far could I have received signals today, starting from the Big Bang. That number would turn out to be of the order of 10 gigaparsec. Okay. So in contrast, the event horizon is something that you ask by starting today. Okay, so remember here, the integral went from 0 to t0. And now the integral is going to start from t0 because I'm throwing the signal from today and I'm asking at infinite time in the future, if such an infinite time is possible for this cosmology, how far would this signal reach? So that is again this integral. It's a very similar integral, just the range of integration has changed. Okay. And again, I can play tricks with these transformations, and I can write this in different ways. Okay, so here I've written, instead of dz over h, I've written it in terms of dA, and now there's an a squared h. And this particular quantity is actually finite in cosmologies with a positive cosmological constant. So this is an interesting aspect of these cosmologies, because if you think about it, if I didn't have any cosmology, right? So suppose I lived in the Minkowski spacetime, just a flat universe, metric is minus dt squared plus dx squared plus dy squared plus dz squared, no time dependence. And now I ask the question, sitting here from today, I throw out a signal of light and I have an infinitely powerful torch. How far away can people see my torchlight? Okay, how far into the future can people see my torchlight? How far away can they be? And the answer is it can be infinitely far in the future at infinite distance from you. Okay, so this distance will tend to infinity if this upper limit goes to infinity in a typical cosmology where there is no expansion. And the reason is simply that there's nothing to stop light from keeping on going forwards except for 1 over r squared dilution. So that's why I said I want an infinite torch so that I can just keep pumping. Okay, enough photons that they will just reach wherever they can reach. And the reason, therefore, that it's interesting to ask the value of this integral is that this value is not always infinite. In universes which have, or in cosmologies which have a positive cosmological constant, this number turns out to be finite. You can calculate its value in terms of the value of the cosmological constant. So again, I invite you to do a little numerical exercise. You have already seen from Surud how to write codes to do these simple integrals. So find your best Pythonic way or any other way to calculate this particular integral. And for h of a, you will have to plug in a particular choice of cosmological parameters, omega m, omega radiation, omega lambda, etc. So see what comes out with this. Okay. All right. So this is what the particle and event horizons are. And a related length scale in the problem, it is not exactly a horizon, but it is a very useful length scale, as we will see in tomorrow's lecture, is called the Hubble Radius, which is just a dimensional argument at this stage for the time being, coming from the fact that the Hubble parameter, which is defined as A dot over A, has units of inverse time, right? Because it is 1 over A dA by dt. So that 1 over dt gives you a unit of inverse time for the Hubble parameter, h. So this h inverse has a unit of time. So c times h inverse, c is the speed of light, c times h inverse has a unit of length. And this is not just a dimensional argument, because it turns out that this is a conceptually very interesting quantity also. The reason being, for one that this h inverse of t, which is, as I said, a quantity with dimensions of time, it gives you the current doubling time of the universe. Okay, so if you ask the question, if today the universe has a certain size, or more precisely, if I take 2 points which are separated by a cosmological distance, let's say 10 megaparsec today, then how long will it take for these 2 points, which are supposed to be the standard observers, co-moving observers, how long will it take for them to be separated by 20 physical megaparsecs, 20 proper megaparsecs, if they were 10 megaparsec today? And the answer to this question is given by h inverse of t. It's the best estimate you can come up with of the time that it will take for a typical cosmological length to double. Okay, so that is h inverse. And more interestingly for us, from the point of view of structure formation, when we study perturbation theory, we will see that this particular length scale, it decides which wavelength modes experience gravitational instability. And I will not have time to give you the mathematical equations which show you this very, very clearly. But instead, I will right away give you a very intuitive and physical understanding of this. Basically, think of it as the following, that space is expanding, right? And the speed of light is finite. So if the expansion of the universe is very rapid, then gravitational instability, which has to work within the framework of general relativity and hence special relativity, nothing about gravitational instability can travel faster than light. Okay, so if my universe is expanding rapidly enough, then there will be places which are separated by such large distances that I will not be able to, so if I create a gravitational instability at one of these points, it will take some time for the other point to realize that there is a gravitational instability that has been created. So even if I set up perturbations which have some wavelength, and this wavelength it happens to be larger than this size of the causal patch, which is defined by the expansion of the universe, then these well-separated points separated by this wavelength will not be able to respond to each other. Okay, so the scale below which gravitational instability can take over is loosely associated with the Hubble radius here. Okay, so this is all I will say about these distances at this stage. So let's go ahead and discuss what I mentioned before, problems with the standard model of cosmology. So the first interesting problem is called the flatness problem. So these are problems that were addressed in the 80s. Okay, so people realized that this is an issue with the standard model. So the first such problem is called the flatness problem, and let's see what the issue is. So we know, and people in the 80s also knew, that the total density parameter, which is just if I take all the matter densities that I can think of, right, matter, radiation, all the stuff that contributes to the right hand side of the Friedman equations, if I take those densities and divide by the critical density today, I will get the total density parameter, omega 0. And this quantity has to be, according to the Friedman equation, this is simply given by 1 minus the corresponding parameter associated with curvature. So I've also put in dark energy, whatever you want here, okay, all the matter-like stuff here, and the right-hand side is purely geometry. So this quantity we know is order unity. Okay, we in fact believe that it is very, very close to 1. We say that omega k0 is actually pretty close to 0. But for the time being, even if omega k0 is not very close to 0, even if it was like plus minus 0.1, for example, this number is still a number of order unity. It's pretty close to 1. That's all we need, because now ask the question, what happens to the total density parameter in the past? So if I call that omega of A and I subtract 1 from it, I will get the negative of the curvature parameter evaluated at that early time. And this curvature parameter at early time, you can just go back to Friedman's equation and ask yourself, what should this look like? And it will turn out that it looks like a ratio of this type. There is a omega k0, which is the current value. And then there is a time dependence, which is given by this ratio. Okay, so if you are careful about this, you will see that there will be an a squared on top. And in the denominator, there will be these particular quantities. The way this happens is because omega k is actually some number divided by a squared. And then that whole thing divided by h squared, because h squared is what you get in the critical density of the universe. Okay, and then I just multiplied out by a to the power 4. So that's why radiation is appearing with no power of a here. And the 1 over a squared, which you might have thought for omega k, it has become an a squared because I multiplied both the numerator and denominator with a to the power 4. Okay, and similarly omega lambda 0, which was a cosmological constant, because I multiplied by a to the power 4, so then there's an a to the power 4 here. So this is just mathematical manipulation of Friedman's equation and the definition of omega k as a function of time. So why am I writing it like this? Because now take the limit where a goes to 0, which is the early time limit, remember. Okay, at early times, a is very small. So as a goes to 0 or as a becomes much less than 1, what happens here? So in the denominator, I have terms like a to the power 4, a squared, and a, and then a constant coming from radiation. So this constant is obviously going to dominate eventually, right? As I make a smaller and smaller, it is only this one that will remain. So in the denominator, all of this time dependence from these three terms will go away. And the whole time dependence will be given like a squared. But this a is itself going to 0. So what have we concluded? That omega minus 1 goes to 0 like a squared as a goes to 0. Good. So now let's ask the question at a specific epoch, for example. Why is this a problem? So take a particular epoch which is well understood. So you went through a lecture on the thermal history of the universe, and you know that the 1 MeV scale, mega electron volt scale epoch, sorry, this V should be capital, which happened around 1 second after the Big Bang. This is a reasonably well understood epoch in the universe. It is the time when electrons and positrons were decoupling from each other. It is the time when neutrinos were decoupling electrons and positrons were annihilating with each other. Neutrinos were decoupling from the relativistic fluid. So this is a very, very standard model time in the history of the universe. But already around this time, according to this logic, if I plug in the numbers and I ask what is omega k0 a squared by omega r0, I know this number today, I know this number today. So in fact, I will just parameterize in terms of omega k0 because omega r0 is a small number and this a is being evaluated at 1 second after the Big Bang. This number is of the order of 10 to the minus 15. Okay, so omega minus 1 is basically different from 0 only in the best case scenario. It is different from 0 in the 15 decimal place, even if omega k0 is a number of order unity. And we know that actually omega k0 itself is tiny. The current constraints are like 10 to the minus 3, right? Plus minus 10 to the minus 3. 0 plus minus 10 to the minus 3. So this is even worse. It's like at least 16 or 17 or 18 here instead of the 15. So this is a big fine-tuning problem. And so why is the early universe, which is otherwise well understood, why is it so finely tuned to be flat? Okay, so it's a fine-tuning issue. Fine-tuning issues are generally a matter of taste. Sometimes high-energy physicists will say that it's a big problem. Other high-energy physicists will say it's not a big problem. But it is still something to make you uncomfortable. When you start seeing numbers like 10 to the minus 15, so it's 0.000 up to 15 decimal places, why should this have happened? Okay, well, and then if you go to earlier times, it becomes even worse because this A will become even smaller. So this is one issue with the universe. The second problem with the universe is not a question of taste. Okay, you cannot just hide it under the rug and say that, but it's not really affecting physics. It's just a fine-tuning issue. This second problem is a problem with causality. It's a problem with very, very fundamental aspects of physics. And it's called the horizon problem. So this is why I wanted to discuss horizons, because the problem is exactly about the size of the co-moving particle horizon, which we discussed. So remember, the co-moving particle horizon is the distance to which signals could have traveled starting from the Big Bang. Okay, so now let's do this calculation. we know that there is an interesting epoch in the universe, which is the epoch of when the photons in the photon baryon plasma decoupled from the baryons because hydrogen formed, right? So the universe was cooling, electrons and protons were moving around and hitting these photons, and they were all forming a relativistic plasma with sound waves. But then because the universe kept cooling, at some point an electron which fell into a hydrogen atom and into a proton and became a hydrogen atom did not have a corresponding high energy photon to kick it out. Okay, so at this point, neutral hydrogen starts forming and remains stable without getting ionized. And once this happens, all the free charges in the universe disappear, and photons in the standard model can only interact with charged particles. So the universe becomes transparent, and this is the epoch at which the cosmic microwave background is released. And we know when this happens. It happens around a redshift of 1100 at a time around 400,000 years after the Big Bang. So now take a standard cosmological model and ask the question, what is the co-moving particle horizon size at this particular epoch? Meaning, what is the distance to which a signal could have traveled starting from the Big Bang and ending at this decoupling epoch? And you do that integral which I told you, plug in your favorite cosmological model with radiation, matter, whatever, and you will get a number which looks like 180 H inverse MPC. Okay, so it's something. Now let us ask the following question. Suppose I have a patch which is of this size, and I observe such a patch today, meaning there are places in the universe which were causally connected by signals that started at the Big Bang, and these signals traversed up to the photon decoupling epoch. So imagine signals that were going in different directions in the sky starting from the Big Bang. I can ask the question, what kind of sphere would they trace? What size of sphere would they trace at the photon decoupling epoch? This sphere would have a radius of around 180 H inverse MPC. So now imagine such a sphere placed in the sky, and now you are observing this sphere somehow. Okay, suppose magically you could observe. I want to ask, what is the angle that this sphere would subtend at my eye today? So in order to do this, I have to calculate what is called the angular diameter distance, which again you have seen, because I know that if I calculate an angular diameter distance and I know the physical distance, then I can take a ratio and that gives me the angle. So let's do that. So I can calculate the angular diameter distance to this particular redshift in the same cosmology in which I did this calculation. And now, of course, the angular diameter distance depends on late time things. It depends on the fact that there's a cosmological constant, etc. So you plug in whatever you like and you calculate this distance. And because we calculated the co-moving particle horizon, I should calculate the co-moving angular diameter distance. And this will turn out to be this particular quantity, dA times 1 plus z. And that will turn out to be a number of order 10 gigaparsec. Okay. So again, I invite you to do these calculations and get these numbers right. So here is a 180 H inverse megaparsec, which is the physical size, and 10 gigaparsec is the angular diameter distance. So if I take the ratio of these two numbers, you can quickly do it on your computers. It will be a number like 1 over 60. Okay, it's like 1 over 56 or something. 56 is 60. So this number is of the order of 1 over 60. So this is the angle in radians. So if I want the angle in degrees, I multiply this by 180 over pi. 180 over pi is also about 60. So this angle, very conveniently, turns out to be about 1 degree. Great. So what is this telling us? It is telling us something extremely interesting, because it says that the cosmic microwave background, whose temperature we measure today, okay, if I think of this cosmic microwave background as having originated from some causal physics in the past, which then, and then the photons got released at the photon decoupling epoch. This particular angle gives me the size in the sky over which the temperature of the cosmic microwave background should remain coherent. Meaning that consider 2 points in the sky which are separated by much more than 1 degree. Okay, let's say I take 2 patches which are separated by 10 degrees in the sky. One this way, one that way. What this calculation is saying is that these 2 patches could not have been in causal contact with each other at the photon decoupling epoch. Why is that? Because in order for them to have been in contact, they should have been closer to each other at the photon decoupling epoch than this number, because this is the largest distance by which two causally connected points could exist at that epoch, right? So if they were separated by less than this number, then they should have subtended an angle to me which is less than 1 degree. That is exactly what this calculation did. So if I see 2 points which are separated by more than 1 degree, or more than, let's say, several times 1 degree, then I am sure that they were not causally connected at the photon decoupling epoch. Okay, so why is this a problem? Well, it's a major problem because we see that the cosmic microwave background temperature is extremely uniform across the entire sky, right? Not 1 degree, 2 degrees. It is uniform from this end to that end, opposite points, right? 360 degrees all over, 180 degrees, exactly opposite. So there is a major problem. Why is the cosmic microwave background so uniform across the sky? And you have to, you have to go back and think a little bit about this because this is a really big issue. It is saying that there is something wrong about the causal structure of the early universe if I assume a standard cosmology. So you can appreciate that this is a much, much bigger problem than the flatness problem. Okay, the flatness problem you can even ignore if you like. You may not be a very good physicist if you ignore it, but you could ignore it and still continue to do physics. But here you cannot continue to do physics if you do not address this issue because you're saying that causality has broken down. Okay, so this was a big problem in the 80s and people started wondering about what to do about it. So let's analyze the problem a little bit more in detail. What is it about the particle horizon mathematically that is that can be associated with this issue? And to fix the problem, what should we do to the causal structure of the spacetime? So here is the particle horizon again, written in this way, 0 to t, and now I have written it in terms of the scale factor. So I have an integral which goes like dA over A times C by AH. This C by AH, remember I told you that C by AH is the Hubble radius at any given epoch. So C by AH, basically if I take any proper distance and I divide it by 1 power of the scale factor, I will get a co-moving distance, right? So C by AH is the co-moving Hubble radius. In a standard cosmology, for example, in the radiation dominated cosmology, this quantity C by AH always increases with time. This is its mathematical structure. For example, during radiation domination, it behaves proportionally to the scale factor. So that means that in this integral, which goes from 0 to the epoch of interest, the contribution of this C by AH at very early times is very suppressed because it is a monotonically increasing function. So at early epochs, it is contributing very less. Okay, so per logarithmic A, because there's a dA by A, it is contributing very little. So that is one way of thinking about the fact that this number is a very small number. You see, if this number were a large number compared to 10 gigaparsec, then I would be fine, right? Because then I could accommodate angles which are much larger than 1 degree. So in order to make this number larger, what can I do? So one possible solution, which turned out to be a very interesting solution for theorists, and it became very popular, and it is now the currently accepted way of thinking about things for most people, is to say that let us say that maybe there is a brief period, not a very long period, but a brief period in the early universe, early enough that it does not spoil other epochs which we know and love, like Big Bang nucleosynthesis, thermal history of the universe, etc. So we go very much earlier than those at very high temperatures, and we introduce a small phase in the universe in which somehow patches which were previously causally connected, for a short time, they become causally disconnected. And in order to do that, you can, what you have to do is to make the co-moving Hubble radius decrease as a function of time. Because if you go back to this argument that I gave before, that the Hubble radius is basically giving you a size beyond which causal effects cannot propagate locally, right? So if I take 2 points which are currently inside the co-moving Hubble radius, okay, and their co-moving separation is less than the current co-moving Hubble radius, and now suppose the co-moving Hubble radius itself becomes small. Okay, suppose it becomes 1/10 of its size. Then these points may find themselves separated by the same co-moving distance because their co-moving distance is constant by construction. But now that co-moving distance at a later time is smaller than the co-moving Hubble radius of that later time. So if such a situation could be engineered, then it would be very interesting, because it would say that I can, mathematically also you can see from here, if I make my co-moving Hubble radius decrease, I can increase this contribution here from early times. Okay, and that is probably what, and you may hope that that is enough to create a large enough particle horizon. So what I want to do is to make the co-moving Hubble radius decrease, at least for a short time, but by a sufficient amount. So how do I do this? Co-moving Hubble radius is 1 over h. H itself is a dot by a. So, if the co-moving Hubble radius has to decrease, then a times h, which is a times a dot by a, this quantity has to increase. So its time derivative must be positive. But this quantity inside the bracket, you can see, is just dA by dt, right? The a's cancel. So I need d2a by dt squared to be bigger than 0. Which means that I need a phase in which the expansion of the universe is accelerating. And this is already, if you have thought about dark energy a little bit, this is like what dark energy is doing. The reasons for invoking dark energy at late times are very different from this. We are not facing a horizon problem. We are facing some other issues. We are facing direct measurements of a double dot, which seem to be positive. But the mathematical structure is very similar. You want a phase in the early epochs now, where this a double dot by a is positive. So just like in the late universe, this could be achieved if the Hubble parameter is approximately constant. So at current epoch, we are approaching a situation where the Hubble parameter becomes dominated by the cosmological constant, and it will therefore become approximately constant. And here in the early epochs, we want a similar situation to arise. And for example, that if my h is approximately constant, that means a dot by a is constant. So a is exponentially increasing with time. So at least for a brief period, I need a exponential. So if h were constant, then it would lead to exponential expansion. And exponential expansion would be fantastic, because this 1 over ah would fall exponentially, right? Because this h would be constant and 1 over a would be a decreasing function, exponentially decreasing function of time. So this is how people were thinking at that time in the 80s, and they came up with models which will achieve this requirement. So typical such models, like I said, they have to operate at epochs in the universe which are otherwise, they should be far from epochs which are otherwise well understood. So you don't want to spoil Big Bang nucleosynthesis. So typical models work at very high temperatures, 10 to the 15 GeV. Okay, this is usually called GUT scale, Grand Unified Theory scale, where things are pretty speculative even now. So it is mostly theoretical stuff, very little observational constraints. And these models will say that around this epoch, which is a scale factor of 10 to the minus 28 or a time of 10 to the minus 32 seconds after the Big Bang, you allow for a phase like this. And this phase is called inflation, because it is a phase of very rapid expansion. And if you can now, okay, so basically if I say that around this time inflation occurred, I have to also ask how long should this phase be, right? How much inflation do I need? So this is easy to estimate, because you can see that if I calculate the co-moving Hubble radius at this epoch, around 10 to the minus 32 seconds, it will be of the order of 10 to the minus 26 of the current value if I assume a standard cosmology. Okay, so what I need to make sure is that there is a phase which increases the, which makes the co-moving Hubble radius decrease, and it expands the universe by basically this amount. Okay, so I have to counter the effect of this fact that this 10 to the minus 26 is a small number. I have to get rid of this number somehow. Okay, and I have to make sure that the co-moving Hubble radius decreases by this amount. So basically, if I want to make sure that the largest observable scales that I can see today are causally connected, I need to account for this much factor, natural log of this much factor, that many number of e-folds of increase in the scale factor. Okay, and simultaneously, I also have to make sure that the Hubble radius at the start of inflation was large enough so that when it decreased by this dramatic amount, the things which it left behind were causally connected just before. Okay, so 2 points were causally connected, and then expansion happened, co-moving Hubble radius decreased, and these points became separated by a scale factor, this amount by which the scale factor changed was of the order of 10 to the power 26. Okay, but they should still have been causally connected before. So it's a strange way of doing things, very theoretical, But interestingly, it leads to very observable consequences. Okay, so some of these I will not be able to discuss, the consequences of inflation in the cosmic microwave background. But what I will discuss is what it implies for the initial conditions of the universe. Okay. So typical models for inflation will invoke what is called a scalar field. The scalar field is like the simplest matter component that one can think of. Okay, because any other components that you think of, if I want to describe electrons, positrons, photons, protons, whatever, I have to invoke mathematical structures which are substantially more complicated than the scalar field. For example, a photon needs to be described by a vector field. Electrons, protons are fermions, so then they need to be described by spinor fields. Okay, so things become more complicated as you start talking about standard model particles, and you have to get into the details of high energy physics in order to describe those fields properly. So the scalar field is like a toy model of matter where I just have a scalar function. I don't have vectors, I don't have spinors, I don't have tensors, etc. Okay, so it turns out to be interesting enough to work with a scalar field to describe inflation. We anyway don't know how inflation worked, so it is good to start with toy models at least, and then see how far you can push the toy models. And these days there are models which will say that, okay, we do know of a scalar field in the universe, which is the Higgs boson. So maybe inflation is related to the Higgs boson. So then there's the idea of Higgs inflation. Okay, so people will talk about such things, but here we are talking about the simplest such model, where there is some scalar field. It is called the inflaton. It's called, and it's denoted by phi. And we say that let us allow this scalar field to have some potential associated with it. The meaning of this is to say that in GR I need to write down an energy momentum tensor for any kind of energy component. So for the scalar field component, I can write down the following energy momentum tensor. This basically follows from symmetry grounds and the fact that there is a postulated potential function. So this potential function can be anything. It will have to have certain dimensions to make sure that this energy momentum tensor has the correct dimensions, but otherwise it can be some functional form which is as yet unconstrained. Okay, and then people will play with different functional forms, or they will motivate this functional form from some other high energy physics or more different theory of graphs. So for example, string theory may lead to some motivation for what this V of phi may be, and so on and so forth. So people play with such things, but the basic idea here is that if I take this energy momentum tensor and I say that this phi depends only on time because I'm describing a smooth and a homogeneous and isotropic universe, then I can immediately calculate the associated density and pressure. So you know that any energy momentum tensor in the homogeneous and isotropic universe can be characterized completely by its energy density and its pressure, both of which are just functions of time. And if this is the energy momentum tensor on the right hand side, then I can calculate the rho and p associated with this phi and v of phi. And it turns out to be this. There is a time derivative of phi squared, both in the density and the pressure. And then there is the potential, which appears with a plus sign here and with a minus sign here. Okay, and this is again a simple exercise. You know what the definition of rho and p are in terms of the energy momentum tensor. So just take this functional form on the right hand side, plug in the definition of rho and p, and you will find this expression. You have to assume that phi does not depend on space. You can even assume that phi depends on space and then ask what that does. Okay, so there will be extra contributions coming from grad phi squared, for example. Okay, so here, remember, our goal is to achieve an epoch in the universe where the Hubble parameter is approximately constant. And we know also mathematically from Friedman's equation that this can happen if the pressure is approximately the negative of the energy density. Okay. Because that will lead to a Friedman equation in which the Hubble parameter will be approximately constant and the scale factor will grow exponentially. And here you can immediately see that if my phi dot squared were much smaller than v of phi, then this term would be negligible on both sides and my rho would be p would be approximately minus rho. Okay. So you want a situation like this, and basically people will construct models where this will be achieved, where the potential dominates. And this is called a slowly rolling scalar field. slowly rolling because the phi dot is much smaller than the potential. So the analogy is with a potential well of gravity in which a particle is moving, and you can think of phi as the location of the particle, and therefore phi dot is its velocity and v of phi is its potential energy. So you can ask what kind of trajectories this particle will obey depending on the potential. Okay, and if the potential is very, very flat, if this v of phi does not change much with phi, then this rho and p will be approximately both related to this constant v of phi, and you will have a situation where phi dot is very small compared to v of phi. But now this is not enough, because if I just allow this to go on forever, then inflation will keep happening. Okay, suppose I made h exactly equal to constant, then a will always be exponentially expanding, and the universe will never be allowed to do any of the stuff which we know that it does. Right? It goes through Big Bang nucleosynthesis, it goes through recombination, it goes through structure formation. None of that would happen if the universe is always inflating. So a successful model of inflation must make inflation end at some time, specifically after roughly 60 e-folds for the arguments that I gave before. And after this inflation ends, then standard model particles need to be generated. So this generation has to happen somehow, and all the entropy which was collected in the inflaton must be dumped into the plasma, and the universe must be reheated. Okay, because what you can appreciate is that if the scale factor is increasing exponentially, right, then all energy densities in the universe, apart from the inflaton, are exponentially decaying away. Any matter that was there, non-relativistic matter that was there during inflation, or any radiation that was there during inflation, would completely decay away like 1 over a cubed or 1 over a4, and a is exponential in time. Right? So this would lead to a very, very cold universe which has only the inflaton. And we know that our universe doesn't have an inflaton. It has electrons, protons, etc. So where do these come from? So the idea is that this inflation should end, standard model particles should get generated, and somehow all the entropy that is collected in the inflaton should be transferred into the plasma, such that the temperature of the plasma rises to around 10 to the 15 GeV, so that standard cosmology can take over from there. And this epoch is called reheating. I'm not an expert on this, but if you're interested, I can give you references where you can find out more about this. This is something that people have to model. Okay? And now one nice thing about inflation. So first of all, remember that inflation was invented to solve the horizon problem. Okay, and it does that very efficiently because it makes d2a by dt squared positive. And we said that this is enough as long as it occurs for at least 60 e-folds. So let's engineer this, and then the horizon problem is solved. That's good. It also ends up solving the flatness problem because, as you can go back and check, if the scale factor is increasing exponentially, then everything in the universe, all energies, etc., everything is decaying away. In particular, the curvature is also decaying away. Okay, so the universe is completely dominated by the inflaton field only, and therefore the total omega is only coming from this inflaton field. There is nothing left from curvature, which behaved like 1 over a squared, and it exponentially decayed away. So that's also very nice, because even though we could have argued about whether or not the flatness problem is a problem, it's nice to see that once the horizon problem is solved by inflation, the flatness problem automatically goes away. Okay. And finally, the most important thing for us, which is the last thing that I will discuss in the remaining 10 minutes or so, is that when you think about what inflation is doing, you can also ask what kind of quantum fluctuations there might have been in such a scalar field. Okay, and there is a well-developed way of mathematically approaching this problem. It is called quantum field theory in curved spacetime. Curved spacetime simply because we are not in a Minkowski universe, we are in a spatially expanding FLRW universe. So you apply those mathematical tools of quantum field theory in this particular curved spacetime, and you can ask if the inflaton is described by this particular homogeneous quantity, homogeneous isotropic quantity, plus tiny quantum fluctuations, what should the nature of those quantum fluctuations be, given that the scale factor is behaving in this exponential way, and so on and so forth. And doing this exercise, which I will not go into details of, it tells you that these quantum fluctuations must have a very particular spectrum, and the spectrum is something that I will discuss in the next slide. And this is extremely useful for cosmology because inflation therefore not only solves the horizon problem for which it was invented and the flatness problem which comes out as a byproduct. As another interesting byproduct, it creates these tiny fluctuations in the initial density field of the universe. So these tiny fluctuations in the inflaton field, they couple to the gravitational potential of the universe, and therefore they become tiny fluctuations in the gravitational potential. And the gravitational potential couples to everything else in the universe, matter, radiation, everything else. So all other species in the universe will start experiencing these tiny fluctuations in their local densities because of these quantum fluctuations that were set down during the epoch of inflation. Okay, and these are the seeds of the large-scale structure. This is what we believe are the seeds of large-scale structure that we see today. So the picture of the CMB that you see, which is anisotropies at the time of the last scattering, which is around 400,000 years after the Big Bang, they themselves had their origin in this way of thinking. They had their origin in these quantum effects at the end of inflation or during inflation. Okay, so let me now end in the last few slides with a statistical description or a description of the statistics of these initial conditions, which is very important in order to understand what happens later during structure formation. Okay, so what I'm going to discuss here will lay down some of the jargon that we use in the structure formation in the large scale structure community, and it will help you hopefully to understand some of the concepts that will come later. Okay, so in the simplest inflationary models of single field, slow roll, single field because there was only one inflaton, slow roll for the reasons I discussed, where the potential is very flat, so phi dot is very small. There are other models of inflation also in which you can replace slow roll with something else, or you can replace single field with multiple fields. There's a whole literature on this. But at least in these simple inflationary models, the prediction for these tiny fluctuations is that they must have a statistical distribution which is almost perfectly given by a Gaussian random field. So what is a Gaussian random field? Gaussian random field you can think of as the association of a number with every position in space. Okay, so my positions in space are labeled by x, and the number that I'm talking about giving to every position x I will call zeta. So I get a field because this is a number as a function of all the positions in space. And the particular function that I'm thinking about, it has a physical meaning also. It is what is called the gauge invariant curvature perturbation. So curvature perturbation because it is something that describes the inhomogeneities of the metric. And this particular quantity, zeta of x, is predicted to have a nearly Gaussian random field structure. So the easiest way that I know of in order to think about Gaussian random fields is to work in Fourier space. Okay, so I hope all of you are familiar with Fourier transforms. So if I have a function zeta of x, x is a vector, then I can write down a three-dimensional Fourier transform of this function of x by saying that this quantity is a linear combination of, with these phase coefficients, of some other number zeta subscript vector k. So this is the Fourier transform. Zeta k is the Fourier transform of zeta of x. Okay, and be careful here. K is a label. Okay, k is the independent variable. Zeta is the quantity. Zeta is the quantity of interest. And the zeta k's are combined using these phase factors e to the I k dot x d3k. So k is another vector in the problem. This is the wave number. If you remember your Fourier transforms, and I integrate over all wave numbers and I do these linear combinations and I get zeta of x. This is the Fourier transform definition. So now if I want to describe a field, I might as well describe it in terms of its Fourier transform coefficients, zeta k. Okay, because if I know all the zeta k's, then I can reconstruct zeta of x from any set of these zeta k's at any given x. So these zeta k's in general are complex numbers. Okay, so they are, remember, zetas are numbers, k is a vector label. So at every vector k, I have a number. And that number is a complex number. So I can write it in the usual complex number form as a real part and an imaginary part. So here a and b are both real quantities. And because zeta depends on k, my a's and b's also depend on k. So I'm just keeping track of that index. Alternately, I can also think of this complex number as an amplitude times a phase. So in this case, the amplitude ak is the quantity. So that depends on k, and this phase phi is a number between 0 to 2 pi, and it also depends on k. So this is how I would write down the Fourier transform of a general field. But my field zeta is also special because at least it is real, right? Zeta is not a complex number. Zeta is a real quantity. It appears in the metric. So I have to impose some conditions on the zeta case so that my zeta becomes real. And these conditions are simple because I just say zeta equal to zeta star, star being the complex conjugate. And then on the right hand side, I apply the complex conjugate. And then I take a subtraction. So if zeta is equal to zeta stars, then zeta minus zeta star is 0. So I do that on the right hand side also. And you can very easily show that this will impose certain conditions on these AKs and BKs. In particular, basically, if I look at zeta k, then I will find that zeta of minus k is nothing but the complex conjugate of zeta k. And that is how I will achieve as a real zeta. So it will give you these particular conditions on the AKs and BKs or capital A and phi. But more interestingly for us, the fact that zeta is predicted to be an almost perfectly Gaussian random field means that these AKs and BKs are random numbers. They are not just numbers that I can pick by hand by setting them to 1 or 0 arbitrarily. I have to give them a certain distribution. Okay, and I hope you have at some point or the other had some exposure to the notion of distributions of random numbers. So in this case, AK and BK are both supposed to be distributed according to the Gaussian distribution. So remember, the Gaussian distribution has a very particular definition. It is defined completely by its mean and its variance. So when I write down this symbol n stands for normal or Gaussian distribution. This number is saying that the mean of this distribution is 0. And the variance is some number p zeta of k, which depends on the magnitude of this wave number k. Okay. So this is to be specified so far. I have not yet told you what this quantity is, but this is an so far unknown function, but it depends only on the magnitude of k. I will tell you why it depends only on the magnitude. But this is a Gaussian distribution of these AKs and BKs. And you can now also prove that if AK and BK are independently drawn from this Gaussian distribution, then capital AK and phi k can also be shown to have the following distribution. They will now not be Gaussian distributed because capital AK has to be at least positive, right? Because it's an amplitude. You can show that capital AK in this particular case is exponentially distributed or Rayleigh distributed, and phi k is just a uniform phase with no correlations between the phases. Okay. So if this structure is satisfied, then you can show that given this AK and BK or this capital A and phi, the zeta that I construct out of it will obey the following relations. The expectation value of zeta will be 0 simply because I have chosen a Gaussian random field with 0 mean. And the 2-point function of zeta, which is the expectation value of zeta multiplied by complex conjugate of zeta evaluated at 2 different k's, it will have this particular structure where this p zeta of k is the same function that I wrote down here. And there is a Dirac delta in k and k prime, which arises because of statistical homogeneity. Okay, so I am demanding that this Gaussian random field be statistically homogeneous, and actually inflation does this for me. Okay, so the quantum effects that I was talking about earlier, they give me a field which is statistically homogeneous, which gives this particular Dirac delta structure here. And it also gives me a field which is statistically isotropic, which is the thing that makes this p zeta depend only on the magnitude of k and not on the vector direction of k. So statistical homogeneity and isotropy are very important assumptions that go into all of cosmology today. And departures from statistical homogeneity and isotropy are something that you can test in the data also. Okay, so there used to be at least people at IUCAA who were working on departures from statistical isotropy. And statistical homogeneity also, in principle, one can think of testing in the data. So inflation will give you this as an output. It will give you a field which is statistically homogeneous and isotropic. And when I say that you can test this, this is to say that, okay, let us not assume that this particular assumption is valid, and let us see to what extent the data supports it. And to date, most of the observations are consistent with statistical homogeneity and isotropy. And this function p zeta of k is called the power spectrum of zeta in this particular case, because it is related to this 2-point function of zeta. And these averages are ensemble averages over the distribution of all of these Fourier coefficients or Fourier modes. Okay. And inflation will make another prediction. Not only will it give you this Dirac delta and the fact that p zeta depends only on mod k, it will also provide for you the shape of this function p zeta of k. And in particular, it will predict these simple models of inflation, predict that p zeta of k should behave like this. If I multiply by k cubed, you can do a dimensional argument here and convince yourself that if zeta of x is dimensionless, and you follow all of these equations that I have written here, you will find that p zeta of k has dimensions of a volume, okay, of length cubed. And it just follows from all of these particular integrals that appear and so on and so forth. And this Dirac delta also has dimensions, etc. So this p zeta of k must have dimensions of volume. So k, which is an inverse length, remember, right? K dot x is dimensionless, so k is inverse length. So k cube p zeta of k is a dimensionless quantity. And this particular function, k cube p zeta, is predicted to have a form which is almost independent of k. It is almost a constant. And the way this is usually parameterized is in terms of this number ns, whose value is close to 1. Okay, so this ns minus 1 is a number pretty close to 0 in these single field slow roll inflation models. And the nice thing is that observationally today we have constrained this number, and it is in fact pretty close to 1. Okay, its value is something like 0.97 or so. So this is a very interesting relation between inflation and observations. There are others which I will not discuss. And this particular spectrum is called a nearly scale invariant power spectrum. Nearly scale invariant because this k cube p zeta is almost independent of the wave number k. Okay, so I'm already over time. So let me just briefly give you a visual demonstration of what a Gaussian random field looks like. The next couple of slides are stolen from Ravi Sheth's lectures from ICTS. I will give you a reference to those in a bit. So here is a Gaussian random field in one dimension in which a particular choice was made for the value of this ns. Okay, so don't worry about what this n is. It is related to that ns, but basically a particular choice was made here. And what is shown here is what happens. See, all these Fourier modes are independent. Okay, because you can see there's a Dirac delta structure in their 2-point function. So if I set k not equal to k prime, the right hand side vanishes. Okay, so only so modes are independent of each other, and that means that I can add one mode at a time in order to construct a field. So here is an example where 25 Fourier modes were added by randomly drawing some numbers, and then on top of this already existing set of 25 Fourier modes, another 25 Fourier modes were added which had higher k values. Okay, so the next 25 Fourier modes were added. So here I am only adding Fourier modes whose k values are small, and here I am adding Fourier modes whose k values are large. And what you can see is very interesting. When I add only the first few small k modes, I get some structure. When I add the next 25 k modes, which have larger k values, but they are still random numbers, the modes themselves are random numbers, I see that overall, the pattern that I see in the red line is sort of maintained, okay, where this thing is going up, this thing is also going up and so on. But a lot of noise is added which has very high frequency. It's going up and down much more rapidly than it was here. I hope you see that. Okay, and this is because the modes that were added here had wave numbers which were larger, k values are larger. So remember that k is a wave number, right? So it is like a frequency. So these frequencies are higher. So that's why you see that the frequency of the jaggedness is also more rapid here. Okay, so this is one example. Here is another example in which the choice of the scale, the exponent of the power spectrum, this k to the power whatever, this is different, and it is much more negative than in the previous case. Much more negative means In the previous case, if p zeta were some kind of function, let's say a flat function as a function of k, and k is increasing here. In this particular case, which I'm showing here, p zeta is a decreasing function. As a function, as k increases, this p zeta decreases, which means that modes which have higher k value have less power in them. The amplitude, the RMS power of their fluctuations is much less if I go to higher k. And you can see that happening here. Because now if I add the first 25 modes which have low k values, I get some structure. If I now add the next 25 modes which have high k, this overall structure is clearly maintained now, right? This long wavelength structure is clearly maintained. What has happened is tiny amounts of high frequency fluctuations are added on top, right? The frequencies are still high, but the amplitude of those high frequency fluctuations is very low. And that is because this power spectrum is very steeply falling as a function of scale. So this is an example. Let me not discuss this because it will take like 5 minutes or so. So instead I will take questions now, and maybe tomorrow I will start with these last 2 slides. So I will stop talking and let me stop sharing my screen and open this thing. So I see only one question in the Google, and there are some questions. There is one question here. So let me see what is the question in Zoom. There are a couple of questions. So can you please explain the transition of matter-dominated era to radiation era to dark energy era? What can be possible era after dark energy? So, okay, so this is something that Surut covered. I can just answer briefly. You got the order inverted. In the standard cosmology, radiation comes first. Okay, radiation-dominated era comes first because it goes like 1 over a to the 4th, right? So 1 over a to the 4th is more important at early times. After that, matter-dominated era comes, which is 1 over a cubed. And we believe today we are in a dark energy or cosmological constant dominated era. If the standard cosmology is what we think it is, then the cosmological constant dominated era is the one that will take over, and there'll be nothing after that. Okay, so the universe will be dominated by lambda or the dark energy, and interesting things will happen. So you can look up some of these papers which talk about what happens to the future of the universe. Because, for example, there is an event horizon in such a universe, and that means that after a certain point of time, we will not receive signals from arbitrarily far away, because there is a maximum distance to which you can send a signal in such a universe. And that means that the universe will become very lonely after some time, right? Because eventually the Milky Way will be the only thing within our horizon, and then we will not be able to see things from outside. So cosmology will be very different at that time also. So I hope that answered that question. As per Big Bang cosmology, is there any preferred direction in CMB which points to the location of Big Bang? Will Big Bang leave observable signature in large-scale structure formation? So 2 separate questions. Okay, so first question, I will answer in 2 different ways. So first of all, Big Bang is not, in the standard model, Big Bang is not supposed to be an event that occurred at a particular place. It is an event that occurred everywhere in the universe at once. It's just that the whole universe at that time was very, very compact. Okay, and Big Bang is just a name. What exactly happened at that time, nobody really knows. Yeah, so people try to develop theories and models. So loop quantum cosmology, loop quantum gravity tries to address this. String theory tries to address it in different ways. Nobody really has a conclusive answer today. We have ideas, but we don't have conclusive answers. But at least this is understood that it is the whole universe which experiences this phenomenon. It's not a particular place. So there is no such direction in the CMB which points to the Big Bang, because that such a location does not exist. But you could ask the question, are there special directions in the CMB itself? So people have asked this question, and this goes to the idea of statistical isotropy that I was talking about. If statistical isotropy is broken, one of the possible signatures is that there may be directions in the sky, and people have looked for such directions. So there is the so-called cold spot in the sky, and the direction defined by the cold spot is an interesting direction. And the people have looked for directions defined by the anisotropy structure of the CMB itself, and so on and so forth. Okay, so this is an active area of research, but currently the best guess is that The universe seems to be consistent with statistical isotropy. There are claimed detections of statistical anisotropy as well. And you can look up some of the literature by the group of Tarun Sauradeep, who used to be at IUCAA. He is at ISSAA Pune now. So his students have produced PhD theses on this topic, and you can look them up in the literature. Okay, so I'll come back to this Zoom question in a bit. Is there something interesting on Google? Where did the universe obtain such a large constant energy to inflate itself, breaking causality? This is a very interesting question. There is no conclusive answer to this. Inflation is something that has to unfortunately be postulated. It has not yet been possible to derive it from first principles, okay? Because there is no known theory which will give you a unique answer for inflation. There are models within the string theory framework that I am aware of, but I'm not an expert on. But I know that people have come up with models where within the string theory language, you can come up with naturally occurring scalar fields, which can behave like inflatons. Okay, and in this case, typically it's not just one. There'll be typically many such scalar fields which will be hanging around in the early universe, and then you can try to achieve the same kind of behavior that you require, which is that the causal horizon, the co-moving particle horizon has to decrease, or rather the co-moving Hubble radius has to decrease. This behavior could be achieved in such models also. Okay, I hope that answered that question. And there is one more question here. Yes, no problem about that inversion. So what is gauge invariant perturbation of curvature? How is it ensured by zeta of x? So zeta of x is the gauge invariant. It is the name given to the gauge invariant perturbation. I should have explained it better. So basically, I'm sorry, I don't have anything to write on. But if you remember the metric, I will show you this in the next lecture anyway. But the metric of the homogeneous and isotropic universe had only a scale factor which depended on time. And there were spatially flat, so there are no other things. If you look at the Cartesian coordinate way of writing this, there are no other spatially dependent components and no other time dependent components also. Okay. Now, this is the homogeneous and isotropic universe. But now if you allow for spatial and temporal fluctuations in this kind of geometry, you can ask, how can I describe them? And you have to be a little bit careful, because in general relativity, there is a coordinate degree of freedom that is given to any user. Okay, so I, as a user, am allowed, as an observer, I'm allowed to change to any convenient coordinate system that I like without affecting the physics. So I have to account for this coordinate degree of freedom, freedom that I am given in GR, in asking what kind of perturbations exist in the early universe or in the late universe. Because if I'm not careful, then I can mistakenly assume that a particular function is describing some very large inhomogeneity, when in fact it could be completely removed by a simple coordinate transformation. Okay, so I have to allow for such effects, and what I get after accounting for such effects are functional degrees of freedom, which cannot be removed by a simple coordinate transformation. So they are the physical degrees of freedom associated with the perturbations in the metric. And this is the gauge invariant perturbation that I was talking about. So in the early universe, there is one such function that one deals with, and it is given a name, zeta, and the inflation scenario makes predictions for the perturbation spectrum of this function. So I hope that was clear. And I don't see any other questions. So we can stop for today, and it's also time for the next lecture probably. So we'll meet tomorrow. There is another question. Maybe you can just post it on the Google form and I will take it up tomorrow. Okay. So if Sagar is there, we will end the recording. Yeah. So I'm done.